So before we hop in and start looking at our data set and fitting our model, I want to talk about logistic regression and what it is, some key details. So obviously, since we're in classification, we know that logistic regression is a classification model. It's commonly used to predict the probability. So when you're thinking about predicting probabilities, it's commonly used to predict the probability that an example belongs to a particular class, given the parameters we learned by the model and the features of that example. So for an example about logistic regression would be, a logistic regression model could predict the probability that a user will click on a particular ad given their previous activity on the site, the content of that page, and the content of the ad. And it may assign a probability of that user clicking on it at that given time to be 32%, or it's a probability, so it's between 0 and 1, 0.32. So that's an example of logistic regression and how you would use it in the real world. The equation for it, logistic regression, is the exact same thing as linear regression. So you're going to fit the same linear regression equation to your data, but the output is going to be transformed. So if you look at this equation here, you have it right here in parentheses on the bottom in the denominator, you have your regular linear regression equation. You have the intercept, which is b naught, plus beta naught, plus beta 1, which is your only parameter here, times x. And so this is a simple linear regression equation right here. And it's inside of these parentheses. But it's embedded in this function, this outer function. And so we're going to transform the output of that. And what we're going to do is we're going to put it inside of this function where it's 1 over 1 plus e to the negative of the output of that linear regression model. And this function that we're embedding the linear regression equation into, this whole entire function here, is called the sigmoid function. And the sigmoid function is going to take the output of this linear regression equation right here, which is a continuous value, like it was in the previous, when we fit a regression model, we saw it as a continuous value. It could be 1,000 or 900 or something like that. It's going to take that output from this right here, and it's going to squeeze it down into a number that's between 0 and 1. And that means it can be interpreted as a probability. So the output of this linear regression equation could be 5,000. But whenever we slam it into this equation, we could get a number that's between 0 and 1, and we can interpret it as a probability. And so that's a brief overview of logistic regression. What I want to move on to right now is I want to talk about how do we calculate the error of our linear logistic regression model, classification models in general. So I mentioned cross entropy loss in the previous slide. Now I want to talk to you about what that actually is. And we're only going to talk about the binary classification case just because this is an introduction and we're trying to keep it as simple as possible. So remember that the loss function is the error of the model on one example in the data set, just one example. The cost is the sum of that loss across all examples in the data set. So this is the loss. Remember that the cost is just summing this up across all examples in the data set that we trained our model on. And so for each example, the model is going to output a probability between 0 and 1. That is going to be here where y pred is, y underscore pred. We're just going to plug that here into the equation. So if the model is 0.9 or something like that, plug it into this equation. And then y is going to be our actual label for that example. And so the actual label could be 1 or 0, right? Because it's classification. It's either two classes, 1 or 0. And so we're going to plug 1 right here. Let's say y is equal to 1. The label is equal to 1. We're going to plug 1 in right here, and then 1 in right here. Or if it's 0, we plug in 0 right here, or 0 right here. But our model's prediction between 0 and 1 goes here, the probability prediction goes here, in y pred, and the actual label goes where y is. And then this ln, if you're familiar with it, is the natural logarithm of our model's prediction here, and then the natural logarithm of 1 minus the model's prediction here. A couple interesting things to note about this is that if the actual label for that example is 1, then this whole side right here collapses to 0 because we plug in the actual label here for y, which is equal to 1. 1 minus 1 is 0, and then 0 times anything is 0. And so if y is equal to 1, the actual label is equal to 1, then we're only using this side right here. If y is equal to 0, the label is equal to 0, this is equal to 0, this collapses to 0. And then this right here is the only side. This evaluates to 1 right here, so this is the only side that we're evaluating for the loss. So that's an interesting property. Also take note of the fact that there's a minus sign out front. And so we're taking the negative of anything in here. And I also want to note that the natural logarithm of 1 is equal to 0, and the natural logarithm of 0 is, it's undefined. It's negative infinity. We're only taking the natural logarithm of our prediction, or 1 minus our prediction. It should never be 0 or 1 exactly. It shouldn't be outputting things like that. It should be close to 1. It should be really close. It could be really close to 1, like 0.99996, or really close to 0, like 0.00001. But it should never be exactly that. So we shouldn't have to worry about this. But if the thing is that imagine that y is equal to 0, and our model's prediction is equal to 1, right? So right here, since y is equal to 0, we don't care about this side. We only care about this side. So y is equal to 0, so this right here is going to be equal to 1. So all we care about is this right here. So our loss is going to be the negative of the natural log of 1 minus our prediction, which was 1. And so 1 minus 1 is 0, and so this whole thing inside these brackets are going to evaluate to the natural log of 0, which is negative infinity. And so the negative of negative infinity you can think of as infinity. And so as you can see that's a really large loss, where our actual y value, the label was 0, our prediction was 1, that's way off, okay? That's going to make the loss really high. And you can do the flip for that. Imagine that the label was 1 and our prediction was really close to 0. Then this number right here is going to be really high. This number right here is going to be 1. And so it's going to be 1 times the natural log of some number really close to 0, which is really, really big, a really big negative number. You multiply it by a negative number and you get a really big number. And so this loss gets bigger the further apart y and y pred is, and that's exactly what we want in a loss function. So that's logistic regression, that's our loss function. Let's hop in to looking at our data set and training our model so we can learn from doing.